Next speaker is Paul Munter. Singularities in minimal submanifolds.
Okay. So I'll talk about singularities in submanifolds, but I mean, why do we care? I think that's a fair question. So the basic sort of idea that underlines everything is we want to find and then subsequently understand submanifolds of a given manifold that obey some variational property, some special thing which we can hopefully use to understand the original manifold. So we want to find and understand manifolds obeying some variational property. And so why do we want to do this? Well, because the simplest example of special submanifold is a geodesic. So this critical point of length. Geodesics are incredibly important, useful in studying Riemannian geometry. So there's many applications of this. So sort of the first example of why you care about this problem is just for the geometric applications. So for example, geodesics, these are critical points of length. And in fact, they're actually better than critical points. They're actually locally length minimizing. So it's things you learn when you first take differential geometry. So also locally length minimizing. But of course, geodesics is just one-dimensional, so you can equally ask, what about a higher dimensional analog of a geodesic? So a higher dimensional analog is what's known as a minimal submanifold or just minimal surface. Surface doesn't necessarily mean two dimensions here. So higher dimensional analog is the minimal surface. And these also then have applications to studying sort of geometry topology. I think Sven maybe here talked about that a couple of days ago. So I guess if anyone's watching on YouTube, then they can check out Sven's talk as well. So yeah, these both geodesics and then the high dimensional analogs, minimal surfaces, have been incredibly useful in studying geometric applications. And another problem of interest, I guess, which is more physical, is that, well, geometric objects that obey a variational property occur very often in nature. Typically, things are governed by some energy minimization, and the force on an object is determined by how a force exerted over the sort of its surface area, and so shapes in nature are governed by these sort of variational properties. So I'll just say nature. And so two examples which I'll just write down, which one of them will be particularly important for us. One is the notion of a bubble, usual bubble. So this is sort of minimizing area for a given volume. And the other is that of the soap film or plateau problem. So here you've got a fixed boundary, and then you're finding the surface that spans the boundary, and which has minimal area. So minimize area for a given boundary. And so this is sort of known historically as Plateau's problem. So yeah, so there's the geometric application, which we'll focus on. I'll talk more about, but then there's also this sort of very natural application as well for these things arising. Okay. So the basic setup is we're going to have a Riemannian manifold. So fix some Riemannian manifold of dimension m plus n. I'm going to be looking at n-dimensional surfaces, so dimension m. So Riemannian manifold. And the two basic questions are then, can we find sort of objects which minimize area in some sense in M? And then what can we say about them? So one, can we find n-dimensional minimizes, area minimizes, I should say, in M. And then two, what can we say about these? So the first way of trying to find one of these minimizers is inspired sort of by the plateau problem, which is that if you have some non-trivial homology class, then you've got some boundary and you can try and minimize the area within the homology class. So if you have some alpha in the n-dimensional homology class of M, which is non-zero, you can try to minimize area in. So, okay, the standard way of doing this would be defining the infimum over all possible elements of the homology class, take some sort of sequence that converges to the infimum, and then try and extract a limit out of this. And in order to do that, you need to be able to extract a limit, so you need to pass to a subsequence that converges. And so you need some sort of compactness theory. And so the world of smooth objects breaks down sort of immediately, and you need to work in sort of a weak formulation of the problem. And this took quite a while to develop, but it was done in the 60s by Federer and Fleming. So for the sort of direct method, you need a compactness theory. And then this is provided by sort of the weak formulation of the problem in terms of so-called currents. Which are essentially just the dual space of differential n forms on the manifold. Okay, so anyone who knows about PDE is familiar with sort of weak solutions for a PDE. So this is sort of a geometric variant of that. So once you've got an appropriate existence theory in the weak sense, the question then becomes, what can you say about the regularity of the object? So how close is this current to actually being a smooth sort of submanifold? So what about the regularity? So I'll just mention two things. One is in the codimension 1 case, so when M is 1, so you're looking at n-dimensional minimizers in an n plus 1 dimensional Riemannian manifold, it was shown that by numerous people that actually this minimizer is smoothly embedded away from a codimension 7 singular set. So set of dimension at most n minus 7. So in particular, if you're in low dimensions, then actually the codimension 1 minimizers are smooth. And in particular, if you're in a 3 manifold then you have smooth geodesics and you have smooth minimal surfaces, which is where this theory is particularly useful in the three-manifold case. And the other thing I wanted to mention is that you could potentially hope that maybe you can do this and avoid singularities altogether, which is a fair question. In code dimension 1 has actually been recent progress. Sort of generically, you can actually improve this to n-9. That's done in the last year. But it's known that actually there are sometimes topological obstructions to actually having complete regularity. So this is actually done originally by Tom. So topological obstructions. Complete regularity. Okay, so you can't hope to have smooth objects always. But then, what was done in this sort of tremendous work in the 1980s by Almgren was that, maybe I should say that, so Tom's work, this counterexample is sort of high codimension and high dimension as well. I think it's 7-dimensional and a 14-manifold or something. But you can ask the question, okay, well, what can I say about the regularity at all? Is there anything I can say? And so what Almgren was able to show is that, so I'll write this as a theorem. Almgren, 83, that this area minimizer is always smoothly embedded outside a codimension 2 singular set. So the singularities are codimension 2. So away from singular set of dimension at most n-2 for any n and m. So for all n.
You really mean embedded, not immersed?
Yeah, this is really embedded. You can't have immersed point, as in codimension 1 crossings, yeah. So Almgren's original proof was very long. It's sort of these sort of typical. It was about 1,000 pages. So Camillo and Manuel, they simplified it. So it was about 300?
200.
Okay. 200 pages?
Font size, our font size is much better than.
That's the whole improvement.
But what was left open for quite a while is, okay, well, an arbitrary set of, if I just have a dimension bound, it can still be very bad. So it could have, you might hope that because these things are sort of natural in some sense, that the singularities should have also some geometric structure to them. And obviously an arbitrary set with just a dimension bound could be very bad. And I mean, Leon Simon has constructed examples which show the thing is kind of as bad as you could hope it to be.
Dimension is also dimension.
Sorry?
Dimension is also
House dimension, yeah. So what we were able to do, so I don't mean to just write this down, so theorem, so this was last year, so this is joint with Camillo, myself and Anna Skorobukatova, and also independently at the same time by Brian Krummel and Nishant Vikramasekaran. That's a bit tight. Is that actually the singular set? It's essentially an n-2 submanifold up to a certain measure theory. So, in fact, the singular set what is called countably n-2 rectifiable. And like I said, this sort of loosely just means it's an n-2 submanifold up to such a measure 0. And then there's some other things in here about uniqueness of tangent cones. But I don't want to get too technical, we'll get into that too much. Okay, so that was the main thing we proved, but I just finished just mentioning a few sort of further natural questions which are still left open from this that you potentially hope for, which is, so this is great because it gives you some geometric structure, but it doesn't actually tell you anything about the measure of the singular set. So for example, in if n was 2, this would be 0-dimensional, and the hope would be, and this is actually known, this is proved, that singularities in that case would be isolated. So you can't have accumulation of singularities. So that is actually known for n is 2, but in general, you could hope for having locally finite measure. So that's one sort of big now open problem.
Now this is n-2 dimensional.
Yeah. And another thing I'll just mention is that, well, all of this sort of minimizing, the sort of finding these minimizers relied on having a non-zero homology class. You can always find not minimizers, but critical points of area in a Riemannian manifold using a different sort of approach than just this sort of minimization procedure based on work of, again, Almgren. So you're able to construct just critical points of area, which are in fact locally stable. And so it'd be nice, because you can always find these things, to also develop some sort of regularity theory for these sort of locally stable. I'd just say locally stable or just critical points in general of area. But this, I mean, this, for just critical points at least, this question's, there's one resolved basically in the 70s, and it's almost done, I think, since. So this seems to be a very hard problem. Okay, but yeah, these are just two sort of natural open questions. And so I'll stop there.
Questions?
In the statement of these theorems, this area minimizer is like in these homology classes, or is it like also for like isochrometric sets, or well, it says area minimizer, so I wasn't sure what.
Yeah, I mean, this I just mean like minimizing in the sense of like if I fix any compact set and I have any sort of competitor, then it's got more, at least as much area. So I mean, you can prove things for isoparametric sets and things like that as well, but that's just the language.
I'm missing something related to this second question. So there is something in your argument that is not local. Because unless I'm missing something there, you're saying that you can take something that is locally stable, so locally minimal and with positive second variation, and still your argument don't apply.
Yeah.
What's that?
Well, I mean, a crucial part of the argument for area minimizers is that you're able to, like, in when you assume, I mean, these local properties are just with respect to deformation. So if you deform the surface by some vector field, then you're a critical point in that sense. Whereas here, this is with respect to any competitor with the same boundary. So here you're able to
Okay. I see the point
surface as long as it's got the same boundary.
it's stable only in the sense of the second variation, not in the sense
Yeah,
of
sorry.
locally minimizing the area.
No.
Okay,
So this
fantastic.
is just the second variation.
So about those topological obstructions to complete regularity, are you talking about that just that there's nothing in the homology class that can be represented by something smooth, or this is particular to the minimal?
So this is saying that there's nothing in the homology class that has the smallest area So in the sense that, yeah, you can't find a smooth thing which has the smallest area in the homology class.
I see, but you can find other things.
You can find, exactly, so you can find singular things which have a single set. Which
No, but I'm asking like if you can kind of find smooth things in the homology class, but they just have a big area, large area. So it makes sense.
Yeah, that happens.
Okay.
Yeah, but it has been proved very, very recently. So there's a PhD student in Princeton that actually proved that in certain particular manifolds, like, I mean, I don't remember exactly the dimension and codimension, but let's say, I don't know, I think already you can take 7-dimensional manifolds with 3-dimensional homology classes inside,
okay,
which if you try to minimize the area, you always get a point singularity, even though the homology class has always smooth. And like, you can't perturb it away in a dense, like, you know, like there's an open subset of metrics
okay.
where this singularity is stubborn and stays there. So now, of course, if you take maybe a very good Riemannian metrics outside of this open set, maybe there is a minimizer which is going to be like, yeah, but it's not something that you can perturb away.
I see. And these are still, this is also because of topological obstruction?
No. So topologically, there would be perfectly regular smooth guys. It's really an analytic obstruction. So essentially, he shows there's for certain particular metric, there's going to be like a minimizer is always going to have a singularity. And then you change the metric and the singularity is stable. So still stiff, you can't perturb it away.
In n equals 2 for your first question, you said that it's proved that the singularities are isolated? Yeah. Okay. Is this a Chang thing? No.
Yeah, it's a short Chang, yeah.
Any more? All right, well, I think we can thank all the speakers in the last 2 weeks, and this is a well-deserved weekend that we all have.